Good morning. This is the regular time slot for the E-VTOL Flight Test Council. We meet alternating Tuesdays at this time, and we have a special occasion this time around. Instead of our usual go-to meeting, we have this webinar. And most of you have registered for it. That's how you got here. So it is a special event. We're not going to do our usual business discussion and so forth, because I want to give as much time as possible to our guest speaker, Dr. Nancy Leveson. And so what I want to do is just kick things off with a short warm-up so everybody understands why we're doing this, why we're doing this special meeting, and why Dr. Leveson is so key for the discussion group. Now, the Flight Test Council has been around since August, and since that time, we've had a number of discussions related to flight test safety, of course, and how are we going to do this new generation of aircraft that are so complex and so integrated. It is not like the old days where you can just have one piece of hardware that fails and the airplane keeps flying, because things are so much more integrated. Now, people in the military world, because of all the complexities there, have been used to this, and they've been doing this kind of work for a while. People in the high-end civil world, Part 25 type aircraft, again, because their levels of complexity, they're looking at this kind of thing. But this is quite new for the small general aviation type aircraft. And it's new to so many people that we thought it would be worth getting everybody up to speed, or at least offering that. And of course, we're going to keep this website recorded. Getting everybody up to speed on what this offers, what STPA offers when we start getting really complicated aircraft. It has nothing to do with the size, it has to do with the software and the complexity. So with that short general intro, let me introduce our speaker, Dr. Nancy Leveson. She has several degrees from UCLA in math and management and computer science. She was a computer science professor at UC Irvine and Boeing. University of Washington in Seattle. She's now at the MIT organization. She's on the faculty of the Aeronautics and Astronautics Board Engineering Systems Division. One of the research used to be new when she started it, and it has to do with software safety. And it's concerned with the problems of building software for real-time systems. And most importantly, it's when the systems go bad that it's catastrophic that we really care. And that's what his ribbon is. She and her students put together the specification requirements, the requirement specs for TCAS-2. So a lot of you aviators are familiar with TCAS-2, and they're applying that. They've started applying that since then to some NASA projects and Next Gen and so forth. Dr. Leveson has released tools, and she has training programs, and she can tell us where to go for more information. To give a sense of the gravitas, in over 20 years ago, almost coming up on 30 years ago, almost now, she got an IEEE Information Systems Award for this kind of work, for developing in the field of software safety, for promoting responsible software and system engineering practices. What she's going to talk to us about applies to all kinds of things, not just aircraft. It is a concept and how it works. And what we've asked Dr. Leveson to do is to give us a 101 level talk so that we flight testers understand what it has to offer, and then we can help push our own organizations, if appropriate, push our own organizations to really get into this. Now, those of you who have been around flight test for a while know that we typically don't get too deep into system safety analysis. Well, folks, times are changing. We need to get deeper into it. We don't have to be the experts, but we need to be wise, and we probably have to push our organizations, because again, this is not normal for Part 23 type airplanes. So with that introduction, I would like to hand it over to Dr. Nancy Leveson for the rest of our show. Doctor?
Great, thank you. Good morning, everyone. I'm just going to give you an introduction as to why this is needed and what it is. It is a training session. At the end, you hopefully will understand vaguely how to do it, but not necessarily be able to do it yourself. So you've carefully thought out all the angles, you've done it 1,000 times, it comes naturally to you, you know what you're doing, it's what you've been trained to do your whole life. Nothing could possibly go wrong, right? Let's start with the definition of safety. An accident, mishap, loss, all of these words are used interchangeably. Is any, in this context, defined very generally as any undesired and unplanned event that results in some kind of a loss. That loss could be human life or injury, which is pretty standard, property damage, also pretty standard, but could also include environmental pollution, mission loss, loss of protected information, negative business impact, and so on. Any works actually for any kind of loss. So it's much more general than most safety definitions. And you'll notice it includes both. It doesn't talk about whether it was on purpose or accidental. So it includes both inadvertent and intentional losses, which means it includes cybersecurity. And the same approach can be used for security. Usually in any system, there's goals and there's constraints. The goals are the mission, the reason you're building the system. The constraints are the limits on how you can achieve those goals. Now, in some systems, the goals are safety, for example, air traffic control. But in most systems, the constraints are really what we're concerned about in safety and cybersecurity. And safety then is just an absence of losses. All right, so let's look at what happened, has been happening in the world here. Get this out of the way. Oh, I can't. Well, there we go. I think I can. Maybe not. So our current analysis techniques that we use are 50 to 70 years old. They're both older than you think. If you look at the timeline here, back in the 1940s, FMEA was invented and started being used. And most of the other accident analysis, hazard analysis, safety analysis techniques were all part of the 1960s. And they assumed that accidents are caused by component failure. But if you look here in the late 70s, all of a sudden the world started changing. And up above, you know, this is with respect to vertical lift vehicles. You know, there was an analog helicopter in the 60s. Personal computers were invented in the 80s. Later on, and in the last 20 years, we have computer-driven helicopters, glass pilots, and now autonomy, teaming, and so on. And what really happened here, if you look at the blue line, is that we started introducing computer control, which resulted in exponential increases in complexity in the vehicles we were building, new technology, changes in the human role. And you'll see the only new technique has been STPA and CAS. CAS is just the equivalent for accident investigation after the fact. But all the other things were built at a time when accidents were very different. And as I said, they assume that accidents are caused by component failure. So let's look at, here's an example. What failed in this accident? So Navy aircraft were ferrying missiles from one location to another. One of the pilots was told, well, if you're just sitting there, why don't you execute this test by aiming at the aircraft in front and firing a dummy missile at them. And of course, these were all friendly aircraft because they were just aircraft just moving missiles from one location, U.S. location, to another. But nobody knew that the software was so-called smart software. And it was designed to substitute a different missile if the one that was commanded to be fired, which in this case was a dummy missile, wasn't in a good position. And there happened to be an antenna between the dummy missile and the target. So the software decided to fire a live missile that was located in a better position instead. And if you look at this, what failed? The software did exactly what it was supposed to be doing. even the pilot did everything he or she was supposed to be doing. Nothing failed. It was a design errors, an error in the requirements, in the interactions between the components. Here's another example. If I can get this to work. This was an Airbus accident, a 320 in Warsaw. It was landing, and during landing, the software protects against activating the reverse thrusters when the aircraft is airborne. So it looks at certain clues the software has to understand to know whether the plane has landed or not. The pilot knows this, but the software doesn't. And it turned out it was raining very hard, and that the wheel turning rate was one of the clues, but that wheel's hydroplaned, got lots of water on the runway. There were other factors affecting weight on wheels and other things that made the software think the plane hadn't landed. So it wouldn't let the pilots activate the reverse thrusters, and it ran off the end of the runway into a small hill, and you can see the results here. Now, basically, there are two types of accidents. There's the standard old accidents that we're all used to dealing with, component failure accidents. But there's also now, we're starting to see these component interaction accidents. They arise in the interactions among the components. In the Warsaw accident, the software did exactly what it was designed to do. The pilot did what he or she was supposed to do. They're related to the complexity or the coupling in our system design, which leads to design and system engineering errors. No components may have failed. They may have, but they don't necessarily. In those two examples, they didn't. They're exacerbated by the introduction of computers and software, but it's not really the software that's the problem. The problem is the complexity of our systems leads to system design errors that we just don't get out. So if you look at this next slide, in the green circle are the scenarios or things that happen that lead to accidents, that involve failures, I'm sorry. So area A is the systems are unreliable, but not necessarily unsafe. Pink is the unsafe scenarios. And if we look at the overlap in area C, these are unreliable and unsafe systems where most hazard analysis techniques work. Fault tree, Hazax, Stpa, all of them work. The problem is in that pink and the section labeled B, which are the unsafe scenarios. They're unsafe, but they're not unreliable. And only Stpa can handle these because it was built to handle it. Here's another accident involving reverse thrusters. This was a totally different plane. This was a Tupolev plane in Moscow in 2012. There was a soft touchdown, which made the runway contact a little later than usual. And there also was a crosswind, so the weight on wheel switches didn't activate and the reverse thruster system wouldn't deploy. Now that sounds like the Moscow accident, but there was a little difference here. In this case, the pilots, believing that the reverse thrusters are deploying like they always do, and having limited runway space because they landed a little late, they quickly engaged high engine power to stop quicker. But instead, because the reverse thrusters didn't come on, it accelerated the plane forward, eventually colliding with a highway embankment. In complex systems, human and technical considerations can't be isolated the way that we usually try to do, unfortunately, nowadays in our systems. We have the human factors and the engineers don't necessarily interact, but they have to, because unless we consider pilot behavior, even normal behavior like this, we're going to be in trouble. So the problem is that human factors usually concentrates on the screen out. Hardware and software engineering concentrate on the screen in. And nobody is looking enough at the integrated system as a whole. So we're getting these new kinds of many more new kinds of errors, like mode confusion on the part of pilots, situational awareness errors, inconsistent behavior of the software in the plane, which confuses the pilots. And we can't just look at the human factors and separate it from the design of the aircraft itself and the design of the logic and the software. And one of the, closely related problem is that the role of humans in these systems is changing. Traditionally, we assume operator errors that cause the most accidents and incidents. Whether it is or not, pilots are going to be blamed. So what do? You do something about the operator, the pilot, or you do something about pilots in general. You marginalize them by putting in more automation, which puts them farther away from the plane and causes more of these same kinds of problems. Or we rigidify their work by creating more rules and procedures that they can't follow and still fly the plane under all conditions. Fumbling for his recline button, Ted unwittingly instigates a disaster. A new systems view of operator error, I believe, is what we should be adopting, where operator error is just a symptom. It's never the cause of an accident. All behavior and human behavior is affected by the context or the system in which it occurs. And the role of operators and the role of pilots is changing, and the errors that they're making is changing. And we're designing systems in which operator error is inevitable, and then we blame the accident on the operators rather than the designers. So the basic bottom line is the human error is a symptom of a system that needs to be redesigned. It's not in itself the final problem. The problem, if you see operators making mistakes, most of the time that can be tied to system design problems. So I believe we need a paradigm change from the old approach. The old approach on the left is that we try and prevent failures. And basically what we do is treat safety as a reliability problem, either a failure on the part of the hardware or the software, or a failure on the part of the the pilot. And instead, what we should do is what's on the right here. Enforce constraints on behavior, but only constraints on the behavior of the components, but constraints on the interactions among the components. And what this basically does is treat safety as a control problem. So what I'm going to do is explain what I mean by control problem and how we would do this. First of all, it's a very broad definition of control. Behavior of a system can be controlled by the human operators, the pilots, or through system design, we can control for component failures and unsafe interactions, or through processes, including test or assurance processes and operational processes, or through various kinds of social controls. And all of these things will need to be used to ensure that we minimize or eliminate accidents in the future. The controls of the controllers enforce safety constraints. Things like, just to show what I mean by that, aircraft must maintain sufficient lift. Aircraft or automobiles must not violate minimum separation. Something that we've unfortunately become too familiar with lately, the public health system must prevent exposure of the public to contaminated water, food products, and viruses. This idea of constraints can be applied to a large number of types of systems. So STAMP, it just stands for System-Theoretic Accident Model and Processes, is a new, more powerful accident loss or loss causality model. The old models say that accidents are caused by chains of failure events, and that just doesn't include the accidents that we're seeing today. So instead, in STAMP, we define accident and losses as a dynamic control problem versus being a failure problem. Now, it turns out this applies to very complex systems, much more complex systems more complex than the systems that we had to deal with in the past, or that the traditional hazard analysis systems can deal with. Stpa has been applied in the most, and is being applied now, in the most complex systems humans have ever tried to build. I mean, we wouldn't even think of trying to use fault trees and these other things on these systems because it just won't work. It includes the scenarios from the traditional hazard analysis methods. The failure events, accidents still could be caused by component failures, so we can't ignore that. But it also includes these component interaction accidents, software and system design errors, human operator errors, and it includes, in fact, the entire socio-technical system, not just the technical parts. And I'll show you an example in a second. And I just want to note that you're not missing, we're not losing anything in this change to this new paradigm. The stamp-based analysis, at the traditional analysis is on the left, you can see, is a subset of the stamp-based analysis. The scenarios created in this analysis will include all the scenarios that are included in the past, but it includes more. And I'll give you some real world examples of where this has been shown to be true. We can show it mathematically too. So if we look at this whole thing, and this chart on the bottom, I say, you know, STAMP is just a theoretical causality model. It's not an analysis technique. But on this model, we can build all kinds of new tools. Accident analysis, something called CAS. What was that?
We just had a little feedback.
Oh, okay.
Our apologies for that.
Okay, that's somebody who's saying something to me. So we can do this accident analysis, CAS. We can do hazard and security analysis, which is STPA. But just to show you, we can do other things. Risk assessment, much more powerful and effective and accurate means of assessing the risk. Organizational cultural analysis. We can identify leading indicators. Often when over time risk increases because the behavior of people, the behavior of other things changes and the environment changes. And risk tends to increase. And we can use this to identify when risk is increasing. We've done this using FOCA data from a very large international airline, and we're able to identify problems before they led to accidents, and various kinds of system engineering techniques. So now let me just focus on STPA. It stands for System-Theoretic Process Analysis. And what is it? What it is an analysis technique that identifies safety and security requirements and constraints. And then from that, it identifies the scenarios or the events that can lead to a violation of those constraints and requirements. And then once we've identified the scenarios, we can use the results to design or redesign the system to be safer. And as I've been pointing out, it finds these hazardous design flaws in addition to just failures, which the other older traditional techniques find. It includes hardware, software, humans, organizational processes, and so on. And I thought I should mention, since most of you are interested in tests, how this could affect tests. And it supports tests in terms of test planning, identifying what tests need to be done, in terms of risk management, managing risks during the testing, and investigating test abnormalities to figure out why they occurred. And in fact, this is being used, I understand, at Eglin Air Force Base and in other people for test planning. So what does it mean to treat safety as a control problem? How does this all work? Well, on the left here, you'll see a diagram. At the top is the controller, and at the bottom is the control process. So the controller could be human and the pilot could be software. The control process is basically the aircraft being controlled for the most part. I also use some more general examples. In the controller issues, this is a feedback control loop, which means that the controller issues control actions like increase thrust or whatever, and gets feedback via sensors that tells us what the result of that control action was, what state the control process is in. Now, here's just the only really technical stuff here. A controller always has both some way of making decisions, but it also, every controller, human or automated, has a process model. The process model is the model of the state of the control process, at least the state that the controller thinks the process is in. And it gets that information about that state from the feedback. And so when it gets feedback, the controller updates its process model. Humans have that too. We all have to. We usually call it a mental model, but that has other kinds of implications. So, and we certainly wouldn't say that software has a mental model. So we just call this a process model. Accidents that are related to software or to humans often occur when the process model is incorrect. That is, it's inconsistent with the real state of the process. So in the Warsaw accident, the software thought that the plane was still airborne, and therefore, so its process model, it had gotten feedback from the weight on wheel sensors and wheel turning things, in other words, that said, this plane is not on the ground, it's still airborne. And so its process model became inconsistent with the control process and wouldn't allow the reverse thrusters to come on. This kind of a model captures software errors, human errors, flawed requirements, and so on. And I'll show you an example of how. Here, remember that here's the reverse, the Warsaw accident, the reverse thrusters. The hazard was inadequate aircraft deceleration after landing, right? So what happened? Well, there was feedback that indicated the plane hasn't landed. So the software process model, the software said the plane hasn't landed. The pilot, of course, his model was correct. And it said, or her model, the plane has landed, right? The pilot knows, they can see it's on the ground. So the pilot issued a command to turn on the reverse thrusters. The software said, I'm going to ignore that command because the plane hasn't landed. All right. That sort of explains not only why this happened, but this is also the process that STPA goes through in doing an analysis. Let's look at the Moscow one. That was where the pilots increased propulsion in order to stop slower. It starts with the same problem. And the hazard's the same, inadequate deceleration after landing. You can see in the top yellow one. And everything else is just the same. But there's more to this one there, because here the pilot's process model said the reverse thrusters are going to come on. It's a short runway. I need more power to stop. So the pilot engaged high engine power. The software controller ignored the reverse thruster command because it says I'm still in the air. But it said, well, there's nothing wrong with engaging high engine power. So it engaged the high engine power. And you could say, oh, well, you know, this is just hindsight. This is after the fact. No, actually, we've had this before. We have to be doing a comparison or evaluation of STPA with SAA ARC 4761, which is the way commercial aircraft, Part 25 aircraft are certified today. And basically, it uses fault trees and probabilistic risk assessment. Now, as we were doing this comparison, and of course, it can't find this kind of problem because nothing failed here. All right, it doesn't, all the components work the way they were supposed to. So, but we found using STPA, we found the scenario and we thought, well, you know, is this kind of weird? I mean, maybe it's, you know, this is just obscure and never happened. So we looked around the web to find out if it had ever happened in operations. And that's when we found the Russian example, the Warsaw example, and in fact, lots of examples. There's one in a military aircraft, all different aircraft. And we were amazed to find so many instances of this in different types of aircraft of this same hazardous scenario. And the problem is that standard hazard analysis cannot find it because there were no component failures. Now, this is just one example. We found hundreds of these things, and I'll tell you in a few minutes some examples on real aircraft that we've done. But how does it really work? How does STPA work? So let me sort of briefly tell you, if this is clear as mud, don't worry about it. We usually spend an hour on this alone when we're trying to teach people to do this, but you're going to get very impatient if I spend too much time on it. So we have this controller here, this model on the left, this control model, and we have these control actions, which I've circled in red. And we start with examining what kinds of unsafe control actions could be given. Well, control commands required for safety aren't given, or unsafe ones are given. Potentially safe ones are given too early or too late, or control stops too soon or is applied too long. The pilot is told to go up to 30,000 feet and overshoots and goes up to 32,000 feet. The actual analysis we do is first we identify potential unsafe control actions. And so we have a way of a process of going through, and it's very structured step-by-step process of identifying the potential unsafe control actions of all of these 4 types. We identify why they may be or were given, and then eliminate or mitigate those from the design. And finally, if safe ones are provided, then why weren't they followed? Let's say that the controller did issue a reverse thruster command, but there was some failure, component hardware failure in the engine, and the reverse thrusters didn't come on. That's a failure down in the control process, and that's what the old traditional hazard analysis methods find, and we will find them too. We will find all of those critical hardware failures. We don't do it like a FMEA and look at every single failure and identify every single failure and say, well, could it be critical? I mean, this on aircraft today with millions of parts, this is not going to be very efficient or effective or even possible always. So what we instead is we only find the ones that can lead to hazards. We don't identify ones that are not hazardous or unsafe. Now, I just want to point out that this is a pretty simple model of humans. And in fact, we have much more sophisticated model. I just didn't want to have time to go into it, of how humans behave. And this is being used in a lot of large companies who are using this for human-computer interaction. For example, General Motors has a policy now that if they have any human automation interaction system, before they're allowed to put it on the cars and sell it, it has to go through an STPA analysis. So one other point I want to make is that the analysis is done on a control structure. So far, I showed you very simple control structures, but what we do is build a control structure for the system being designed. This is right now with respect to vertical lift, we're doing a whole lot of work in urban air mobility and also in the Army Future Vertical Lift Program, FARA, and some of the other vehicles that are being designed. This is just what the model that we would use to do the analysis, say, for UAM. And you'll notice at the top here, we even include the regulatory agencies, including and government, local government, because they're part of the problem, as we've seen in some of the recent big, well-known aircraft accidents. We include air traffic control right over there on the left. There's conventional aircraft up in the air over on the bottom right. The stuff that I just put in purple shaded it because it's part of the, directly part of UAM. There's on the top left there's a support infrastructure, aerodrome operators, data providers, navigation and tracking, ground services. That right is PSU, that's just the service providers, which may have humans and software in them. Underneath them, being controlled by them, are the fleet operators. Underneath them are the actual UAM aircraft. And what we will do is identify the control actions first, and then do this STPA on this to find out what the potential hazards are so that they can be eliminated from the system. Here's another one. This is from a more military defense oriented problem. We have maintenance and pre-flight over on the left on the top that I didn't have in the other one. We also have a lot of teaming here. What's happening now, and I'm sure you're all aware, is not only are humans controlling the software on their own aircraft, but they're also teaming with automated aircraft. It's not like the human is controlling the automated aircraft. It could be that they're just both controlling separate things. The software and the human may be both controlling the same thing, or they may be controlling different vehicles or aircraft that are supposed to coordinate or need to coordinate and to cooperate in order to achieve some common goal. And this kind of teaming and process is just not even, I don't know how you would do this in the traditional methods, but we're doing this now for these kinds of complex systems. So this is just some example results that we have just with respect to teaming. So for example, there may be conflicting commands for multiple controllers. So we have to find out how that would happen and make sure it isn't that the design prevents it. There may be an improper handoff across boundaries. There may be machine teaming semantic problems. There may be workload problems that prohibits teaming. There may be flawed team planning and execution. There may be trust issues. This is a real problem. How do we get the human pilots to trust the automated team member that they're teaming with? Incompatible system configurations, the mission's too dynamic to effectively plan it because the mission is changing continually, but we still have to make it safe. Those are just some examples of the kinds of problems that STPA can handle. Now, what this does is, and I haven't mentioned security, I've just been talking about safety, so I do want to mention security because this allows an integrated approach to safety and security. Both of them are concerned with losses, and one, the losses are intentional, the other, they're unintentional, but it doesn't really matter if the operator is does the wrong thing unintentionally, or they're tricked into doing the wrong thing, for example, by some kind of intruder. They're both involved in mission assurance versus mostly information protection. As a pilot, you're interested in making sure, and the engineers are in making sure that the mission is accomplished, not that some enemy is stealing the social security number of the pilot. That's not the problem here. And so what we want to do is ensure that critical functions and services are maintained, or that bad things don't happen, like friendly fire. So it turns out that this new paradigm for safety and this new technique, STPA, will work for security too. We have to add some new causes, but the rest of the process is totally the same. And both of them allow us to build this top-down system engineering approach to designing safety and security into systems. The old traditional analysis methods require that there be a design before you can do the analysis. That's not true for STPA. It can start at the very, very beginning of concept development. So you can identify problems before you've designed them and have to undesign them, because it's just incredibly expensive if you change your basic design. Who's using this? Well, currently, it's being used in just about everything. Aviation, I would say, I'm not sure exactly. It's the FAA is talking about allowing it for certification very soon, so it will go up a lot. Automobiles, there's already standards, they're already using it. I would guess 80 to 90% of automobile companies, especially autonomous automotive companies, autonomous automobile companies, are using this. Virtually everyone in automobiles, because the old techniques just aren't working. It's being very widely used in defense. The Air Force is using it in some of their most complex systems. As I said, it's being used in testing and other kinds of activities at Eglin and other places. And the Army is starting to use it in future vertical lift and require it on their new future vertical lift vehicles. We're now assisting them in analyzing designs and using STPA for it. But it's used in all these other things less commonly. At the bottom, you can see we were shocked. Last year, we had a SAMP virtual workshop, and we had over 2,300 registered people for this workshop from 73 countries. I would guess of the 2,000, about 1,000 of them were aviation and defense. So it was about half was aviation defense, and automobiles was a large number too, and the rest were a smaller number, although more and more people in other areas and other fields are starting to use this. There are standards, auto, aircraft, and defense standards that either already exist, have been created, or they're in development for STPA. So does it work? I mean, people may be using it, but does it work? Well, it turns out there have been hundreds of evaluations and comparisons with the traditional approach that are used now. People don't like the idea of changing what they're doing. They're scared about changing when the thing is safety critical. So they want to test it. And so most companies do sort of parallel developments, but there's also been some very scientific evaluations and that have done on this. Every single one that was done in any scientific way show that STPA is better. It identifies more critical requirements or design flaws. There have been a couple. I mean, there are hundreds of these now. There have been a couple that I saw, but the people didn't know STPA, and so they didn't do STPA. They did FMEA in the form of STPA, and then said, well, I didn't find anything more than FMEA did. Well, of course, because you didn't do STPA, you just did FMEA. It has identified real accidents that other methods missed. EPRI, the Electric Power Research Institute, which is the power companies, including nuclear power, did an experiment where they gave a design of a nuclear power plant safety system, shutdown system, to has up to experts, to fault tree experts, to FMEA and FMECA experts, to event tree experts, everything that they could think of that had ever been suggested for use. And then they also gave this to two of my graduate students to analyze using STPA. And it turned out nobody knew until afterwards. At people said, well, there had been a real serious accident in this nuclear power plant design, and only STPA found it. And the problem was, it was a design error, and only STPA could have found it. Everyone that's measured shows that STPA requires order of magnitude fewer resources. This shocked me because I assumed it was more powerful. It finds more. It's got to be more expensive. And what we're finding is, after people learn it, you know, the first couple times it probably costs the same as the other, but after that, there's a tremendous exponential decrease in cost, and it is orders of magnitude cheaper than the others because it does it in a different way. Return on investment estimates are only beginning. One large defense industry contractor claims to have saved billions of dollars by using STPA. And how did they make the savings? Well, because they could find the problems during concept development, potential problems, and not design them in. We all know that the other techniques have to wait until you have a design. We all know that the later you find errors, the more expensive it is to fix them. And that's how they were able to save so much money with it. So let me just give you a couple examples. One was that I'm allowed to talk about in public because it's been published. This was the Blackhawk. It was an upgrade to the Blackhawk of a new warning, caution, and advisory system. So we analyzed it with STPA, and then we compared the results with the independently conducted hazard analysis of this upgrade using the traditional safety processes that are described in ARC 4761, the thing used by aircraft, commercial aircraft, and MIL standard 882E, which is the military standard for safety. And STPA found all the same causes as the traditional techniques found, but it also identified many things that weren't found using traditional methods, including design flaws, potential human behavior that could lead to accidents, and component integration and interaction types of accidents. We also found that because they'd also done a risk assessment, you know, the red, green, yellow charts, and many of the hazards they had identified, or failures they had identified as marginal, STPA found scenarios involving those failures or hazards that were actually catastrophic. The marginal ones would have been ignored. The catastrophic would say you better do something about this during development. Here's another. This is a dynamic positioning system. They ran into each other twice during tests. And so we performed this cast analysis. That's an accident analysis on the two accident incidents. And then we used STPA on the system as a whole. And we found all kinds of scenarios that weren't found by the MIL Standard 82 analysis, which were fault trees and FMEA. And the engineers were very excited about this, that had asked us to do this, and they took this. We went to a Navy admiral in charge of the system, and he said, well, we've used PR probabilistic risk assessment for 40 years. It just works fine. We don't need all this fancy new stuff. So they ignored us. They put the system into operation, And within 2 months, one of these escort vehicles ran into a submarine. And the reason I know about it is extensive damage enough to get into the newspapers. So I immediately called my friend, one of the engineers on the project, and I said, what happened? And he described what happened. And I said, well, that was one of the scenarios we told you about. We identified that beforehand. He said, yeah, well, so this keeps happening. We're finding these things that aren't found by the traditional methods. So, as I said, I was just about finished anyway. Here's some more information. There's at the very top of the screen is a website with papers, presentations from conferences and workshops, tutorial slides, tutorial videos, all kinds of examples, and so on. They're also up, you can get, on the left is my book, Engineering a Safer World, came out in 2012, beginning of 2012. You can get a free download. I made a deal with MIT Press, the publisher. If you go to that website, they do a good job of hiding it, but it's there. There is a free PDF download button there. In the middle, there's an Stpa Handbook. That's up on the website at the top. That's also free. There have been over 100,000 downloads of this Stpa Handbook in the last 30 months. In case you want it, there are Japanese, Chinese, and Korean versions up there, which are from which were just engineers created them and then asked us if we'd put them up there. So, which was fine with us. The other we have is a CAST handbook, which is how to learn more from the things that do happen. It also has a free download. We just got a Korean version of that was sent to me from some engineer in Korea who created it. So that was, I think, all I have. So I can answer questions if you want.
Absolutely. Let me, while everyone else is putting their questions together, let me go ahead and kick off with a simple one. Since there are not enough system safety experts to go around to all of the E-VTOL startups out there around the planet, they're going to have to grow their own talent in a lot of cases. Can you give us a sense of how much investment there is to be competent in this so that they can get, presuming the authorities want this for certification, about how much of an investment is it to get there?
Okay, an SCPA class is about 3 to 4 days, full time for a day, and that includes the engineers doing lots of examples themselves on their own systems so that they get practice. It's not teaching it. Takes about a day. The other 2-3 days are spent in practicing it. But it turns out, as I said, it turns out to be easier than the old methods. Because I teach the old methods and I've been doing system safety for 40 years. I teach the old methods, I teach the new one, STPA, and I have to tell you, it's so much easier teaching STPA to the students at MIT who are bright students. But the most interesting part, I think, is that STPA is best done not necessarily by system safety experts, but by system engineers and system experts. We have pilots doing STPA. We have system engineers doing it. And it's back better because what's happened over the years, when system safety started in the 50s and 60s, it was part of system engineering. But for some reason, it's been separated and isolated from the system engineering effort. And that's not good because you don't find the errors then until the very end when it's so expensive to fix and maybe impossible to fix at that point. So what we're teaching people to do is to put an STPA expert in as sort of a facilitator in the system engineering group while the system engineers are learning it, and to actually have system engineers are doing this and working with this facilitator. And it may be that the facilitator first creates the table of unsafe control actions, and then the engineers just review it and say, oh yeah, that's right. Oh, you forgot this. There's this. I think, oh wow, we didn't even think about that. Is the kind of response we're seeing, and so some detail work may be done by a few experts, but this can really be done by system engineers. Now, again, it may be more efficient work-wise to have some people assigned to do this as opposed to just making your project manager is not going to want to, or your program manager is not going to want to sit and do this. But what we found is that the top, when we come to the group of system engineers with these things, okay, review this with us, that they're really willing to do it, and they learn a lot, and it's worked tremendously well. So it's not like fault tree analysis. This is much more intuitively obvious and actually easier to do once you learn it.
Okay. Well, thank you. You definitely set the hook. And I'm gonna bite more, and I'm gonna bring my organization to get into this a little bit smarter and see if we get us a couple of ninjas on this to lead those discussions. All right. Well, let's see who else has some questions. Raise your hand, or we can look through the chat. Chris, we're gonna go ahead and look through that. The questions here. And Chris, can you open the line so that callers can talk? Mute.
Sure, yeah. So we could do that a couple different ways, Al. We could have people press the raise your hand option, and that'll tell us if they want to speak, or we could open everyone's line. I'm not sure if I recommend that fully.
We have over 100 folks. Let's go ahead and let's do the raise your hand thing.
Sure.
So folks, if anybody has questions, just raise your hand and Chris will let you in, and you can go ahead and speak. Or you can type it into the chat. I'm reading there. If anything should show up.
Okay, it looks like we have a hand raised from Anthony. I'm going to go ahead and unmute here. Anthony, you're now on the line.
Hi, Anthony.
Hi, how are you? Very good brief, Nancy. Thank you. My background is in operational test and also in the Navy, so I appreciated the brief. So, and this is Tony Pucciarella from Alaris Pro. So my question is, how are you documenting this? So as you have these scenarios, and as you, I'm assuming it's not a just a large paper of use cases and scenarios and outputs. How do you document this as you start feeding in some of your fault tree analysis and everything else? Are you using like goal structure notation as a supporting factor of this? How do you document all this as you pull it together?
This is just documented in, well, we use tabular forms, mostly tables, to do it. There are lots of tools that are or have been created. I'm not sure I love all of them. The Japanese government just created one for a free tool for everyone in Japan or elsewhere to download. It has, all of them. It's sort of new, so I think the tools aren't all great. But it's documented mostly in tables because we found that that's the easiest way for people to find things. But we haven't spent a lot of time on the human factors part of documentation. Yeah.
Okay. Thank you.
But as I said, there are tools. The
the biggest part you need a tool for is drawing the control structure. And we just use drawing tools. We use Visio and other drawing tools. Sometimes we use Excel. But other people have created some drawing tools.
Okay, thank you. All right, looks like we got about 4 or 5 more questions. Maybe let's do David Whitburn next.
Sure, I'll go ahead and unmute him.
Yep.
David, you are now on the line.
First of all, I just want to say thank you to the professor for giving us this information. I'm a United Airlines 737 pilot, flew the MAX 9, and currently on a leave of absence working for NASA System Safety Group, looking at the 3 different lunar lander designs. So we are doing the traditional system safety. So I'm kind of blown away that there's this stepping forward in the right direction, and I'm just intimately familiar with the potential for the unsafe actions, both the computer component level, like the MAX, and the human error. I guess my question is, this is probably not the first time someone's asked, how would you introduce this to your superiors? I just wanted to know. I mean, I'm sold. I would love to start training now and implement this now. So, any advice?
This is, of course, very difficult to get people, especially management, to buy into new methods. There's a lot of lethargy in terms of disincentive to create anything new. By the way, I find that pilots are our biggest fans. Pilots love this. And especially I have a friend who's a pilot with FedEx who also is getting a PhD in human factors, and he's using this in his dissertation. He's just totally sold. And has sold it in FedEx. FedEx is using it a fair amount. They were skeptical at first, their safety person, and they said, well, okay, I'll try this. Just cast analysis on one of our incidents, but it's not going to find anything. And he came back to me, and I said, okay, well, I'll try it. And he came back the next a few months later, and he said, Nancy, he said, and we tried it on 2 of them. We found so many more things than we had found before. And actually, we tried it on a 3rd, and we weren't finding anything that we hadn't found in the other 2, but we were finding things that we just never were able to find before or think of, including problems, organizational problems. I mean, it's easy to blame the pilot for everything. It's a lot harder to see that there are real design errors in the aircraft, that are design flaws that are really contributing to behaviors, the unsafe behaviors that people are making, that they're organizational problems. The FAA, and we're working both with them with respect to certification, but also with respect now to UAM and how they would regulate UAM, how you would define a system that would be able to, including all the social and legal aspects, that will be able to protect the public. But as I said, pilots really appreciate this because they're the ones getting blamed for all this stuff that's not their fault.
I would think that if the authorities favor this, even if it's not a formal requirement, if much like with ACs, advisory circulars, if they say we find favor with this is an approved path, that might go a long way towards helping it for the eVTOL community. I don't know if there's any official movement in that direction.
There are. There's a lot. Yes, you're right. The authorities are liking it. And, you know, a lot of them are, their hands are tied somewhat. For example, the FAA has so much policy stuff and things that they have to deal with. But someone at the FAA, they are moving very quickly to allow aircraft certification using Stpa. And one told me that's their highest priority for this next year, is to make sure. And it's just a matter of they have to get certain standards in place. They have to change policy, and it just takes a while in the bureaucracy to make the changes. The Air Force is quickly adopting this on their most complex projects. For example, GBSD and some of the other things. They aren't building new aircraft right now, but they are testing them, and it's being used, as I say, in the test in the Air Force. The Army is using this in future vertical lift and is requiring their contractors to use it. And one of the things they've asked us to do is help them write contracting language, appropriate contracting language. So you're right. The authorities are seeing this as a way out. With automobiles, which isn't necessarily this group's main interest, but the NHTSA and Department of Transportation have just no idea what to do about these automated automobiles. And I actually had a student write a master's thesis on how they would certify and regulate and oversee the introduction of automated vehicles on the nation's highways.
So thank you for all that. Let's go to Scott Newman. You have a question, Scott?
Great. Okay. One of the things I think that test pilots are often asked to do is to evaluate a system, an aircraft in particular, based on the abilities of an average pilot. So, and since that's part of that's sort of an explicit part of your model there, how do you account for or model what an average pilot would be versus an experienced pilot or a young or inexperienced pilot? How do you work that in so that you're able to determine if it's just a particular accident or is just subject to a particular pilot population?
Well, I'm not sure we do. You could. I'm not sure I want to. What I want to do is build the system so that every pilot can be can be improve their behavior. So the basic idea here is that instead of focusing on human error and human inability, what we do is say human behavior is influenced by the context in which it occurs. If you're given certain information that you need to make a better decision, any pilot, most pilots hopefully, can learn to use that information. If you're given bad information, it doesn't matter, or you're not given the information you need, that's the feedback part, then it doesn't matter how good a pilot you are. You know, if you don't know that something has happened in your aircraft, you're not going to be able to respond in enough time because the more experienced pilots aren't necessarily mind readers. So the goal is to build a system to support pilots in general, to make them all better and to support decision making by providing the information and the capabilities that are needed to fly this aircraft safely.
Okay, so if I can ask just a quick follow-up. So, for example, in the 737 MAX, one of the conditions that contributed to the problems was that the pilots that were involved greatly exceeded the maximum speed for the airplane. So would that be, in this system, would that be caught as a potential scenario even though that's not what you wouldn't necessarily expect that as a typical pilot behavior.
Okay, I missed the pilots. What did what? I missed that part.
Yeah, the pilots in those they left the engines up at full power, so they were far in excess of the maximum speed of the airplane had been designed to go, and so that led to some of the control problems.
Absolutely, but the pilots were confused, and they were confused by poor feedback, which has been added. There was not, there were some information, but it was optional for the aircraft and not included in some of the accident aircraft, right? There was very poor training and inadequate training of the pilots because, Boeing was trying to compete with the Airbus, and they were trying to and sell to low-cost airlines around the world, and so they wanted to minimize the amount of training that the pilots were required to do. So it's a complicated problem. I've tried to avoid writing about this, just to keep myself sort of out of the fray. I can tell you that the FAA, we know informally the FAA used it, and it used Stpa and in the investigation of the MAX accident. And we teach classes. They've asked us to teach class every 6 months. We teach certification people, Stpa, although they can't officially use it. They find it really useful to help in the evaluation of the aircraft. So I'm trying to remember, I think I may have deviated away from the original question. I think that that there was a lot of problems in the Lion Air. There was a horrible culture. There was some poor training, but also some problems with pilots being overworked and falsifying records of pilots. There's a lot of stuff that comes up that influences this and influences pilot behavior.
Thank you.
Okay, how about Peter Lyons? Peter always has clever questions.
Okay, Peter. You appear to be self-muted, but when you unmute, you'll be on the line.
Peter, may
Peter, are you there?
How about Pooch? Anthony Pucciarelli. Oh, we got Peter. Peter's on. Off.
Oh, lovely.
All right. Actually, you know what? There we go. I'm hearing somebody.
That may have just been feedback. I don't think that Peter is on the line.
Okay.
All
right.
It appears as though we have some other hands that have gone up. So if you like to choose, I'll go ahead and unmute them.
Yeah, let's try Paul Stanley. He's got a question mark next to his name.
Alrighty, I'll go ahead and unmute him. Paul, you're on the line.
Hi, thanks for the presentation, Dr. Leveson. I understand the power of Stpa to identify causal scenarios that can lead to the losses. Is there any contribution from Stpa to evaluating, say, the relative likelihood of those scenarios, or does that require more traditional methods?
Oh, so to prioritize the scenarios? Yeah, that has come up. Now, some of it's prioritized by the priority of the hazard. So this is completely traceable. every one of the scenarios, all the unsafe, are all traceable back to the original hazards, and then vice versa, you can trace the hazards to all the scenarios. And a lot of times there are just certain hazards that are going to be higher priority. So that would prioritize some of the scenarios. We've also found that there are certain changes that can be made that just eliminate a whole bunch of the scenarios. You know, one change eliminates, 100 scenarios. But we haven't come up with, and we're trying to think about that, how we would, beyond that, how we would prioritize what was the easiest. There may be, especially if the stuff is found late, it may be that you want to prioritize the things that are the cheapest and the easiest to fix, and things that are really going to take a long time and they require redesigning the aircraft is not going to be the highest priority. But we're really focused on doing these things early, during the design, before design, and to use the analysis to guide the design to design safety in, so that the cost is not really a problem at the beginning. It's almost free, which is why STP is so much cheaper, because it's not the cost to do the analysis. The costs come in making changes. But if you design it right to begin with, you don't need to make the changes later. And you use this to design your training procedures. You use this to design your feedback, your control panels, all of these things are designed from the very beginning to ensure that these things won't happen. So we're not finding that there's a tremendous need to prioritize. There's a tremendous need to find these things so we can design the system correctly safely from the very beginning.
Nice. It's a good, solid answer. Thank you. I see Alec Aleph. You've been had your hand up for quite a while now. Can see if Alec is still with us.
Okay, Alec, you should be on the line when you unmute.
Yes, thank you. And thank you for the presentation. I've got a background in flight test, latterly unmanned aircraft and software test. The question I have in this day of agile approaches, Scrum, that sort of thing, have you had any experience of using STPA with those sort of design approaches?
Well, I'm a software engineering expert. That's what my PhD is in, and I'm not thrilled with Agile. I think Agile has limited uses, and its use on large, complex, long-lived programs is going to bite everyone in the butt at the end. You need to identify. Look, if we're going to Silicon Valley, which is where Agile came from, they don't care about if something goes wrong with their website and you have to go log in again as a user. I mean, you don't even care that much. I mean, but we do care about aircraft falling out of the sky, and so there's a difference. If in the Silicon Valley, they can fix it. They use the user as a beta tester, as a tester basically, to get the errors out. We can't use pilots and aircraft, especially normal operations, as a way of testing and getting the errors out of systems, the critical problems. It's got to be designed right quickly, originally, because these things are going to last for decades, some of them, these systems. And we're going to be limited in the amount of changes we can make, because the F-35 is sort of an example. And if we don't designing it right and getting the things out originally, getting the requirements, getting these safety requirements, safety constraints identified before you start designing this thing, it's going to save you oodles of money. Oodles. That's why, you know, these companies are talking about saving 15 to 20% of contract prices, big contracts. These are mostly defense companies, by using STPA. I mean, the total price. So one company told me they had about a $900 million defense system, and they used STPA, and they did a parallel project, and with the regular standard stuff, because they were sort of nervous about using STPA, and so was the Air Force. And they found that they saved $127 million out of this $900 million contract by doing STPA early and designing the things right to begin with. So there are some okay things with Agile, and some things not so great. By the way, we're just about to start because they're all mostly in tests, with the Pentagon. The Test and Eval organization wants to do a comparison of the use of the standard test development process, test case development process against the STPA, and we're going to start that on a project that's in real testing phase right now, a real project, not experimental. So there is interest high up in the Pentagon in using this within the testing community and test process.
Okay.
Thank you.
So, folks, we've been going 90 minutes, and I hate to keep imposing. We still have 90 people on the call, or 86 people. Dr. Leveson, do you still have a few more minutes? Or
yeah.
We tapped everything? Okay. In that case, let's go ahead and unmute James Maxwell, the famous James Maxwell, no less.
Okay, James, you should be on the line.
Hi, thanks again for a great presentation. I'm a flight test engineer at Bombardier. By my previous life, I was in reliability and safety engineering. So I've seen a lot of the theoretical side of things, but now I've also gotten a lot of hands-on experience as well. So my question is, adding on to, I believe it was Scott's question with respect to how an average pilot might respond to a situation. So isn't STPA ultimately still bounded by engineers or pilots' imagination, like when the analysis is being conducted? Because while it may not always be true, many failures manifest themselves from failure of the design team to imagine all the variables and how they might all come together, like the standard Swiss cheese model.
I think you're right. Every analysis method is limited by the imagination of the analyst, but there's some differences. Like fault trees are done in the analyst's mind. There's no model that it's performed on. It's in the mind. The tree itself is just the result of the analysis that's performed. You can't even guarantee that the multiple people working on this analysis even have the same model that they're thinking of. STPA is different in that it works on a concrete model that's on paper. There is a set of step-by-step process that you go through in order to develop the analysis. And again, you start with this model. In fact, what we found is most people find the biggest problems just looking at the model. They, oh, wait a minute, that's what we got? Wait a minute, that can't work. So there's having a concrete model on paper that you're working from, and everybody is agreeing to, has agreed to, and sees as the model is a real benefit. But I would no more guarantee. I mean, there's no way I tell you this is the perfect technique and you're going to find everything. That would be irresponsible of me and incorrect, because there's no perfect analysis method beyond a few mathematical things built on physics. But this isn't built on physics. And so It isn't perfect. All we can guarantee, and I will guarantee this, that if it's done correctly, you know, if it's done by people who know what they're doing, have been trained in it, that they will find more problems than using the old techniques. That's all I can guarantee. I can't guarantee perfection. I don't think we have that. And we can't even, you know, we're always making assumptions about how the world is going to work, how other things, you know, the future, how pilots will behave. These are assumptions that we just, there are always going to be problems in making such assumptions. But as I said, in every case where we've done careful comparisons, we or other people have done careful comparisons, they've always found more this way. So that I'm pretty sure of. I'm pretty sure we'll find more. I certainly wouldn't say we will find everything. The other thing that is really important, and the people like GM and others who have a lot of user interface problems, is that it allows a common language between the human factors people and the engineers. And I think that's also critical. The human factors people don't speak the same language as engineers, I found, and they tend to just separate into two groups, and there's very little communication. In some groups, probably more, and that's wonderful. If it works in your organization, if you really have tremendous communication, and then the human factors experts and the software designers and the hardware designers work daily together. But often that is true. And what this does is provide the human factors people can understand this model. They can use this. We've shown this over and over again without special engineering training. So that it provides it as the sort of interface language, this ability for the human factors, the pilots who may not be engineers or trained in human factors, but understand how to fly and the problems of flying, and all of these people to speak in a common language and to get together to solve the problems together.
Great, thanks so much.
That's great. Let's switch over to Kalyan. Oh, okay, I'm gonna try this again. Kalyanaram. Please correct my pronunciation and talk to us.
Okay, you should now be on the line.
Kalyana Raman, are you with us? Okay. We still have Peter Lyon's name. Peter, have you come back aboard? I still got see your hand up. Okay.
Peter appears to be self-muted.
Oh.
See, there is Alec, who is still self-muted. Okay. All right.
Yeah.
Other than that, I do not see any hands.
Okay. We have a number of too many written questions to go through, but they will be available for download after the presentation. We will get them to Nancy. I don't have, for those of you who are not part of the Flight Test Council, I don't have your email address, so it'll be a little hard for me to answer those questions at this point. So I'll do what I can. I will, I'll tell you what, if any of you have questions and you want some answers, you can contact me directly and I will tie you in. Of course, you have Dr. Leveson's contact info there. And you can contact me at sfte@alawless.com if you are not already on the council. sfte@alawless.com. We can start a conversation. You can join this council, or we can just get you some quick answers. So at this point, I would like to go ahead and wrap it all up. Nancy, thank you so much. Wow, this I think really will turn us around. It opens up a lot of eyes, and people can see that this is probably the way of the future and we better get smart on it now before the train hits us. So with no further ado, I'll go ahead and release everybody. So you still got a couple minutes for lunch, and we'll go from there. Did you have any parting words?
I want to thank you all for your attention.
Yeah, absolutely. Okay, take care, everybody.
Okay, thank you all for attending, and with that, I'll go ahead and end the webinar.